and originally from Australia, but she's been in this country many years. And no one British. Are you British? What did you actually do in Australia? Anyway, Michael. She did have some time in Australia, and she's a senior lecturer at St Andrews. So over to you, Colva, and thank you very much.
Thanks, Beatrice, and thanks to the organisers for I've had a wonderful couple of days. Must admit, I was a bit unsure about coming to a Women in Maths conference because I've never done so before, but I've had a surprisingly good time, and I can see that lots of the rest of you have been getting huge benefit from it as well. So thanks very much to Beatrice and to Gwyneth and to everyone else who's been involved in organising it. Okay, so let me start with telling you a little bit about my career. I don't think I've had a particularly unusual career, actually. So 1993 to 1997, I did my undergrad at St Andrews. I went initially to do maths and philosophy, to do English and philosophy. Took maths as my third subject in first year. In Scotland, you take 3 subjects. I'd done further maths A level, so I thought that would be a nice DOS. And then surprised myself when I got to university, discovering that, in fact, the study of mathematics was far more creative and imaginative than I had expected it to be. It became more and more about problem solving and less about rote applications of techniques as it had been at school. And that the academic study of English literature was far less imaginative than I'd expected it to be, and it was far less about reading beautiful literature and far more about reading rather turgid academic criticism. So a career swerve in my second year occurred, and I switched to a maths degree. So then I graduated from St Andrews. My then boyfriend was looking for a job. We were discussing where best to move so that it was as likely as possible that we could both wind up in the same place. London seemed like an obvious choice. So in discussion with people at St Andrews who recommended Queen Mary as being a great place to do group theory and Peter Cameron as being an outstanding supervisor, I went down to Queen Mary. Spent 4 years doing finite permutation groups for my PhD. Then there was a sticky patch at the end of it, so I submitted my thesis in April of 2001 and had a while of spending my savings, living off my new boyfriend, having rubbish teaching jobs and barely getting by. I think I had given myself a deadline of the end of 2001 to get an academic job before I was going to quit and go off and try and become a computer programmer. The computer programming thing hadn't featured at all in my PhD. It was entirely accidental. My new boyfriend, who's still boyfriend, was a computer programmer, and I wanted to understand what he did all day, so I started reading Knuth's Principles of Programming, got chatting to a wonderful person in the Queen Mary Maths department called Charles Leedham Green, who introduced me to computational group theory, which seemed really interesting, despite being nothing to do with my PhD and was tying into this new interest. And then thanks to Charles Leedham Green, I got a job at the University of Sydney in the computational algebra group. So from about 3 months after first taking an interest in computational mathematics, I suddenly found myself a computational group theorist and in the University of Sydney, which really had never, ever, ever been the plan. So I had a couple of years in Sydney. The first year we had long-distance relationship going on. That was all rather awkward. Second year, my boyfriend quit his job in London and came over to be in Australia with me. He couldn't work. He came over on a young person's working holiday visa because we were both still under 30, but that meant he could only have a job for 6 weeks at a stretch, and he didn't want a job for just 6 weeks. But fortunately, he had given up a very highly paid job to come and be with me in Australia, so he had enough savings that he could just be out there for a bit. Now he's Scottish and was very keen to come back to Scotland, so just as I was beginning to really wonder what was going to happen to me, an email came through from St Andrews saying, "Would you like a job?" To which I duly replied, "Yes, thank you very much." And even more to my surprise, I find myself suddenly a postdoc in the Department of Computer Science doing artificial intelligence, which really hadn't featured in the plan. But I was applying symmetries to backtrack search problems. So artificial intelligence, searching sort of combinatorial type problems you should think about. They often have symmetries. The idea was, can we inject some group theory into the search for solutions to these things to avoid wasting time looking at non-solutions, and also when you found one solution, find all the rest. Well, just after I got to St Andrews, a university lectureship was advertised, about 2 months afterwards, and I said, should I apply for practice? And they said, no, there's no point, it's too soon, so I didn't. 6 months after that, another one came up, and I said, should I apply for practice? And they said, oh, well, I suppose for practice you might as well have a go at going through the application process. Much to my surprise, I got the lectureship, and then deferred for a year because I was really enjoying being a postdoc. Now, quite a few of you are still PhD students. I think postdoc years are fantastic. It's the most freedom you're likely to have until you make it right through to the later stages of your career again. Lots of freedom to travel, no real teaching responsibilities, no real administration responsibilities. It's great. But anyway, it all ended after not all that long, and I became a lecturer back in maths because having been in comp sci, it was fun, but I'd never had a gut feeling for it, if that makes sense. I could do it, but it wasn't ever going to be my first love. So since 2005, I've been a lecturer, and more recently a senior lecturer in pure maths at the University of St Andrews. So along the way, other things I've done, this is something which actually I think it's possibly quite easy to get a foot in the door with as a woman, is doing outreach work. So I started out writing some articles for PLUS magazine, again just via a friend who works for PLUS magazine here based at the University of Cambridge, and I said, can I have a go at writing an article for you? And she said, sure, and it went in. And then coming out of that, lots and lots of other good things have come. So doing radio shows like In Our Time, giving the LMS popular lecture a couple of years ago. It all came out of being enthusiastic and leaving myself open to serendipitous accidents. So the first radio show happened because somebody else in the department got phoned up and asked if they wanted to do it. They said no, but I know a girl who talks. So that was the beginning of my glorious media career, such as it is. Other things I've done along the way is get involved in mathematical societies. So I started out as the St Andrews rep on the Edinburgh Math Society Council. It sort of rotates around among the junior staff. We all do a 2-3 year bit. As part of that, I got more interested in the ways in which mathematical societies can help all of us in our careers, and interested to experience maths as a body of people working together to fulfill similar aims, not just the purely intellectual bit, which obviously one has to love, but the social side of being a mathematician and all that involves as well. So I've now been on the council of the LMS for 3 years. I stood once, didn't get elected, stood a second time, did get elected, and then I've just been re-elected. And then finally another little bit of it is since, I can't remember, 2007, 2008, I've been an editorial advisor for one of the LMS journals, which means I can reject papers or I can find referees and recommend acceptance, and usually that happens. If you get the opportunity to do something like that, grab it with both hands. It's enriched my mathematics so much. Like many people, I am not very good at making the time to read articles which aren't immediately relevant to what I'm doing, and there's nothing like having one a week landing on your desk for you to look at to encourage you to broaden your mathematical knowledge. Now, my PhD supervisor, all the way back at Queen Mary, encouraged me to constantly seek to broaden my mathematical interests, and I've been trying to do that ever since. At the same time, I've spent a lot of time working to develop bits of math that I know an awful lot about, to have a real comfort zone where I can say, I am probably the world expert in this very narrowly defined thing, and then having got that, to look further around and go, okay, I can have a really, really amateurish go at doing all these other things as well. And I think trying to balance that, being a real expert at something, but being able to reach out to all sorts of other bits of maths, makes for a more fun career, shall we say. Because after all, we're meant to be having fun, right? What it's about. Okay, so on to the maths. I'm going to tell you some stuff about group theory, some of which I've done, some of which I haven't done. I'm going to try and keep it reasonably non-technical, because I know that not all of you are group theorists by any stretch of the imagination. So let's start with some definitions. So a group for us is just a set with a multiplication and inversion. I'm not going to go through the axioms, but most of the groups I'm going to be talking about are either groups of permutations, so you've got permutations of some set, you can multiply them, you can invert them. We're going to be interested a lot in subgroups. So a subgroup is just one group sitting inside another one. I've got a couple of technical definitions on this first slide, and then it gets easier. So I say that a subgroup, a smaller group inside a bigger one, is normal in that bigger one if whenever I take something from the bigger group, invert it, multiply by the thing in the smaller group, and then do the original thing, G inverse HG, I wind up back in H. So if that happens every time I pick an H from H and a G from anywhere, then H is normal in G, and I have that little funny triangular box symbol for it. Now the key thing about normal subgroups is that you can in some sense divide out by them. You can decide you're going to work modulo them, You're going to treat everything in that normal subgroup as the identity, and we write it like division G over H. The groups I care about are the simple groups. Now, a group is simple if it doesn't have any of these special subgroups. If the only normal subgroups inside it are itself, because if you look at that definition, obviously, if I'm picking elements from the whole of G and doing that, then it's going to work. And the identity, because if I'm only going to put the identity in the middle there, then the G inverse and the G are going to cancel and I get the identity back. So they're always there. If those are the only ones, then G's simple. So for example, if P is a prime number, like 5, and we take addition mod 5, well, you can't find any normal subgroups inside there. The only one you're going to have is the identity in the whole thing. Why am I going on about this? Well, because understanding the simple groups tells us about all groups. So all finite groups have a series of normal subgroups called a composition series, with the property that whenever I look at one of the things in the series and divide out by the next thing in the series, I get a simple group. So I can break any group down into simple groups. So for example, taking addition mod 6, addition mod 2, which looks like 0 and 3 when I'm working mod 6 is a normal subgroup inside that, because 3 plus 3 is 6, which is 0. Quotients out by that, and I get a copy of Z3, so I've got 1, Z2, Z6, and there's my simple quotients. They're both prime, so those are both simple groups. Okay, so simple groups are the building blocks. So most of this talk is going to be about simple groups. Simple groups come in all sorts of flavors. They've been classified. There's infinitely many of them, but the amazing thing is that we know what they are. There's a lot we still don't know about them, but here's a lovely theorem. So it was proved for the alternating groups by Dixon in '69. Cantor and Lebotsky then did most of the remaining cases, and Liebeck and Shalev finished off with the hard ones. And it says if G is a finite simple group, then I'm going to write by P of G the probability that if I pick just 2 symmetries from G randomly and combine them together in all possible ways, see what I get. Do I get the whole thing? So if by combining those 2 random elements in all possible ways I get the whole group, then we say that they generate the group. Then in fact, as my simple group gets bigger and bigger and bigger, the probability that just 2 random elements generate the whole group gets closer and closer to 1. This is really surprising. You would think that the bigger the simple group, the less likely it was that just taking 2 random elements was going to make the whole thing. But in fact, it turns out that the bigger the simple group is, the more likely it is that any 2 random elements generate the whole thing. So this is a beautiful theorem. It's going to reappear again towards the end of the talk. Let me talk instead about how I got interested in this bit of maths, because I got interested in it from a slightly unexpected direction. So I came in via what's called the Matrix Group Recognition Project. So this is computational group theory. This is a project that's been going for about 20 years now. It seeks to solve a fairly simple sounding problem. So you're given just a bunch of matrices, n by n inversible matrices over some finite field. So everything's finite. What do you want to do with these matrices? You want to know about the group that they make when you combine them in all possible ways. What group do they generate? Well, we want to construct a composition series for the group that they generate, so a way of breaking it down into simple groups. And we want to construct what's called a constructive membership test. So it's a membership test, and it's constructive. What does that mean? Well, the membership test means I'm given something that might be in the group. I'm given an n by n matrix over my particular finite field that I'm thinking about, and the question is, can I make it out of those symmetries x1 through xk, or can't I? If I can, I want a proof of that. I want some actual way of multiplying together the x1 up to xk and their inverses to make my matrix X. If not, I just want to know it's not in there. So it's a membership test. It says yes if you're in the group that they generate, no if you're not, but it's constructive in that if you're in, it comes back with a proof. Why do we want to do that? Well, because loads of other things can then be fitted on top. If you've got this composition series, for example, you know now how big G is. When you've got the composition series and the membership test, you can fit on all sorts of other group theory algorithms to let you answer more complicated questions about what this group is. When you've got these 2, lots of the rest follows. So that's the goal. How are we going to do it? Well, it turns out it's quite hard, but we can now nearly do it. We're going to slowly construct something called a composition tree for the group. So I told you what a composition series is. That's all these normal subgroups with all the quotients being simple. A tree is a bit like that, but it's a tree-like object. So the vertices are going to correspond to bits of G, sections, technically, don't worry, they're just bits of G. We're going to make it as a tree. So we start with G itself. We don't know what G is. We just know that G is generated by these matrices, but we don't yet have any notion of what G is. We're going to work by repeatedly making children of our vertices. Well, we make a homomorphism, phi. So a homomorphism is just a map that respects the group multiplication. There's nothing more than that. So coming down one way from G, I'm going to have the image of this map. Now the thing with maps on groups is they might map a whole load of elements of G down to the identity in this image. It's going to be some other group. So the other child is the kernel. So I'm calling that K, which is the kernel of phi. So that's all of the elements which are going to go to the identity when I hit them with the map phi. Now a key thing about group theory is that this is a normal subgroup of G. So this is something that G maps to, and this is a normal subgroup of G. They're both groups, so iterate. You eventually stop when you get down to cyclic groups, so that's just integers modulo something or other under addition, or quasi-simple groups. So that's not quite simple groups, but it's fairly close to simple groups. So we just carry on doing that. Well, here's a natural question. Working out phi is fine, and working out im phi is fine, but I need some way of getting hold of that other child in the tree. I need some way of getting hold of that normal subgroup, K. I don't yet know what G is, because the whole purpose is to find out what G is, so I can't assume anything much about G. So what I can do is I can make random elements of this group K. There's a trick that lets me land in there uniformly at random. So here's a question. How many random elements do I need to make to be sure that when I combine those random elements in all possible ways, I've actually got K? I've not just got a bit of K, I've got the whole of K. And with some failure probability. All of these algorithms are randomized, so I want the user to be able to specify how willing they are to have the thing fail, how long they're willing to wait, and I want to be able to guarantee that with no more probability of failure than that epsilon that they've specified, I have now made enough random elements of K that I can now treat K in the same way as I'm treating the whole of G, and we carry on until the whole tree's filled in. Okay, well that then was something I was really interested in. I've been involved in constructing these homomorphisms phi in various different cases, and I knew how to do lots of those, and in some sense that situation was under control, but the question of how to make the kernels was really not. So this motivates a more general question. Given any epsilon between 0 and 1, and any group, so let's imagine we're given it as a set of matrices or a set of permutations, and we're going to combine them in all possible ways, how many random elements of that group do I need to generate the group with failure probability bounded by phi? How many random matrices do I need to write down? How many random permutations do I need to write down if I want them to generate G? Okay, I'm going to denote that number by d upper epsilon of G. So d upper epsilon of G is the number of elements of G I need to make to generate G with failure probability of most epsilon. I'm going to denote the smallest number of elements that generate G by just d of G. So I've got G with some bunch of generators, but it could well be that I can make G with just 2, say. Quite often just 2 is enough. So I'll write that as d of G. Okay, so let's think about that. We'll think about that first in the context of permutation groups. So this is just groups given by permutations. That's it. You multiply them together and invert them. Well, there's a theorem in a paper due to Peter Cameron, Ron Solomon, and Alexandra Terrell, but they credit it to Peter Neumann. So apparently he never bothered writing it up, but they needed it for something else, so they wrote it up. And it says if you pick any old subgroup of the symmetric group on n variables, so that's just permutations on numbers 1 up to n, if I've got any old subgroup of that, then if it's not the full symmetric group on 3 symbols, sim3, then I don't need any more than n over 2 permutations to make it. So in terms of the number of points it's moving around, I don't need to know anything other than about G than that. N over 2 is going to suffice. And that's best possible. Here's an example. If I just take cyclic group of order 2, swapping 2 symbols, well, I could take the one that swaps 1 and 2, the one that swaps 3 and 4, the one that swaps 5 and 6, all the way up. That's a subgroup of the symmetric group on n variables, and I've taken n over 2 of those little transpositions, and it's isomorphic to a vector space, right? It looks like f2 to the n over 2. So the minimum number of generators is the same as the dimension of the vector space, and so I need at least n over 2 there. So you're not going to improve that. And undergraduate exercise, sim3 needs 2 generators. It's not cyclic, so we can't do it with just 1, so we need 2. So you need 2 permutations. Well, n over 2 is a lot. When I'm making trees like this, the complexity for everything under here, say, is going to be multiplied by the number of generators I've got. So I'd really rather not pick something as big as n over 2. So can we do any better than n over 2? We know we can't in general. So can we define ourselves into a subclass of permutation groups such that we can do better with that subclass? Well, the obvious family you might think of are the transitive groups. So group of permutations is transitive. So it's moving points around. It's permutations. We're permuting. All right. If given any one point and given any other point, I can find some symmetry in my group that maps the first point to the second one, then I say that it's transitive. It's a nice, well-understood class of permutation groups. What can we do to improve that theorem if we say we're just going to look at the transitive groups? Well, same paper. At G now, rather than just being any old group of permutations, it's a transitive group of permutations. And let's assume n's at least 5. How much better can we do than n over 2? Not much. We can turn our less than or equals into a less than. Not very significant. And we gain some extra exceptions. So there's lots of exceptions for n equals 2, 3, and 4. And then there's this funny exception for n equals 8 as well. So really not looking very good. So what do? We look for a smaller class of permutation groups and hope that for further restrictions we can say something more sensible. So we're going to restrict down to what are called primitive permutation groups. So let me tell you first of all about imprimitive permutation groups, because I'm afraid this is one of those kind of negative definitions, if that makes sense. So I've got my permutation group, and it's acting on the whole of 1 up to n, and delta is somewhere inside 1 up to n. If whenever I hit delta with G, so delta is just some bunch of points, either I wind up back inside delta again, or I completely miss it. So delta to the G is all the way over there. Then I say that delta is a block for G. You can think then of the whole space 1 up to n as being partitioned up into these copies of delta. If that doesn't happen, then we say that G is primitive. So G is primitive if it's transitive, and the only blocks you get are the singletons, because obviously if you've just got one point, it's either being mapped to itself or it's being mapped to some other point, so you get this property trivially, or the whole thing, because the whole thing always gets mapped to itself, so that's also trivially primitive. Okay, so what can we do with that? Well, there's a nice asymptotic result here. It says there exists a constant C such that if I take any primitive subgroup of a symmetric group, then the minimum number of generators is no more than C times log n over the square root of log n. Square root of log n is the slowest growing function I have ever encountered in real life. It's just terrifyingly slow. So basically this is saying log n. Now this is a nice result, but it's useless for me writing code because I don't know what C is. They've not tried to work out what C is. It's not enough to know that I need some multiple of log n. I need to tell the computer how many you can do. So we looked at this problem and generalized slightly further. So this is about to appear. You can think of this as being about normal subgroups of primitive groups. So it's not, that includes primitive groups because any group is normal in itself, but it also includes further ones. For the subnormal just means I'm allowed to take a normal subgroup of a normal subgroup of a normal subgroup, so it might not be normal in the whole thing. So if we consider those, then the minimum number of generators is just plain log n. So the constant is 1, which is quite a nice constant. And we get the same exception that we saw before on the transitive groups thing, unless n is 3 and g is S3, because it needs 2. Now that bound's actually tight. We can construct examples that hit the log n example, hit the log n number. So this was particularly pleasing. It's a very nice formula, that. Okay. So the behavior I'd like you to remember is that for the initial class of groups we thought of, we had linear numbers of minimal generators. We had n over 2, either less than or equal to or strictly less than. Once we've gone up to this subclass, which is primitive groups, we've suddenly dropped to logarithmic numbers of generators. This is a real improvement. So a lot of the time when we're working with groups on computer, we can break them down into primitive groups, and then we know that we only need logarithmically many for each bit. Okay, oh, and it's best possible. There you go, there's my example. Let's talk about matrix groups. The reason we did the permutation groups one was that sometimes this phi and m phi might actually send you to a permutation group, so you somehow need to do both at the same time. So now we're on matrix groups. Well, here's a matrix group. So that's n by n matrices. I've just got the identity in the top left block, got the identity in the bottom right block, zeros above the diagonal, any old junk you like below the diagonal. All right, that's a group. Kind of unfortunate, that group, because that group is isomorphic to a vector space. It's isomorphic to the additive group of the field, looking like SP to the E, where we're working over GFP to the E, to the power n squared on 4. So you're not going to be able to do any better than n squared on 4 generators for it. That's really, really nasty. I mean, if the permutation group's case was bad and we went linear, this is even worse. We've gone quadratic. That's just going to kill us complexity-wise. We're talking about, matrices dimension 100 by 100. I do not want to be taking 100 squared generators in any way, shape, or form. So let's define ourselves out of the problem and get away from being quadratic in the dimension. So the equivalent for matrix groups of transitive permutation groups are the irreducible matrix groups. They're the matrix groups that don't fix any proper subspace of their vector space. So I can't find some bunch of vectors spanning something or other such that whenever I hit them by group elements, I stay inside that subspace. If I can't do that, I'm irreducible. It's completely reducible if the whole thing breaks up into a bunch of irreducible components. So you probably want to think of it in this kind of matrix form. When I conjugate G, I get diagonal things. So these are little squares, and it's all broken down into little squares down the diagonal, zeros above and zeros below. These are nice. So what can we do for generating these? Well, there's an old theorem here due to Kovacs and Robinson from 1991, which says that if I take an arbitrary field, could be characteristic 0, could be characteristic p, could be finite, could be infinite, whatever, and I take a finite subgroup of the general linear group, so a finite group sitting inside there, and assume that it's completely reducible. So in particular, that gets rid of that nasty example that I showed you on the previous page. That's very much not completely reducible. If I take a completely reducible subgroup, then the minimal number of generators is suddenly only 3n on 2. So we've gone from quadratic in the dimension to linear in the dimension. That's really good. And as they point out in their paper, that bound is in some sense best possible, because if f contains a primitive fourth root of unity, so that's like square root of -1 would be a primitive fourth root of unity, you take it to the power 4, you get the identity, then you can write down something which hits this in 2 by 2 matrices, and then you can block them out along the diagonal, and you're going to wind up with a completely reducible group. Each bit needs 3 generators, you can't glue them together, so you need 3n on 2 in the end. Best possible. Well, we looked at their example, and we really couldn't see a way of generalizing their example without using this primitive fourth root of unity. It just didn't seem to work. There wasn't anything else kicking around that worked. So we were then able to say, well, one of the things I would know if this was a matrix group is what the field is, because my matrices are written down over it. So in particular, I know whether or not I've got a primitive fourth root of 1. I don't know what the group is, but I'll know that it's completely reducible. That I can test for, and I'll know what the field is. So if I assume I've got a finite completely reducible group, that's just some notation, that's the scalar matrices. Well, if it doesn't have a fourth root of 1 in the field, if there is no square root of -1 in there, then my 3n on 2 turns again into the nicest constant of all, which is 1. Even better, if I restrict to what are called quasi-primitive groups, they're analogous to these ones. I'm not going to give you the definition because it's kind of technical, but they are playing the role for matrix groups that primitive permutation groups do. So with primitive permutation groups, if you remember, we got down to a logarithmic bound of the number of points we were acting on. Same thing happens here. So that's a really messy looking formula. 2 times log to the base 3 of n rounded up plus 1. That was a pig. It's a proof by induction, and you're having to deal with the rounding ups and +1s, which is really not what you want to be going on, but it goes through eventually. And then if we do even further, when I'm making these trees, I'm coming down through normal subgroups. So if I'm simply contained in a finite quasi-primitive group via a sequence of normal subgroups, then my constant's much nicer. It's just 2 log n. So we've seen similar behavior to in the permutation group case, but one of the things that's really nice here is that when you're talking about groups of matrices, you need to talk about a dimension and a field, always. These bounds don't feature the field. Well, this one features does it have a force root of 1 or not, but these bounds don't feature the field at all, which is surprising somehow. You would think that the field would have more of a role to play in what the group structure's like, but no, it doesn't. Okay, I talked a bit about minimal generation. I started out talking to you about random generation. What have these things got to do with each other? Okay, let's bring it together. So, if you recall, d upper epsilon of g is the minimum number of matrices or permutations or whatever I need to pick such that they generate g. I've multiplied them together in all possible ways. I get g with failure probability at most epsilon. Well, here's a lovely theorem due to Alex Lubotsky. He was interested in proving another conjecture, but he showed that if you want to generate g with success probability 1 over e, so e is the base of natural logarithms. So for me, that would be failure probability 1 minus 1 over e. Then the number of random elements you need to take is no more than the minimum number of elements plus twice log of the group order. That's growing pretty slowly. Plus a slightly mysterious number, 4.02. So thanks to a very helpful referee's comment on an earlier version of our paper, we went and looked at this. A bit odd. 4.02. And you pull the proof apart. Well, I'm going to write CL of G for what's called the chief length of G. It's like the composition length. Think of the composition length. That's the number of terms in one of these composition series. It's the number of simple groups you're breaking it up into. The chief length is very like that, but it's a bit smaller. Okay, then I can't really credit us for this theorem because it's just copying Lubotsky's and writing it in more generality. But now we can say if you have any failure probability you like, and let t be such that the Riemann zeta function of t is no more than 1 plus epsilon. The Riemann zeta function is going down. So how much t do I need to get myself inside 1 plus epsilon? One of the key things here is that this parameter t is going to grow like log of 1 over epsilon. That's the way that the Riemann zeta function goes. Then the minimal number of generators you need to generate G with failure probability no more than epsilon is the number you need for the absolute minimum plus twice the log of the chief length. So it's a bit like the composition length, doubled, plus 2 plus this mysterious t. And if you plug in epsilon is 1 minus 1 over e, then 2 plus t comes out to be 4.02. That's what the mysterious number is coming from. So this says if we can get good bounds on the minimal number of generators, and we can get good bounds on the chief length, which we have done, but I'm not going to tell you about because that's much more technical, then we can get good bounds on the random number of generators that are going to be enough to generate this group with bounded failure probability. All right, so that was that stuff. So the game in this bit has been, you know how your group is represented. You know, say, that it's a permutation group on endpoints, or it's a matrix group of some dimension over a field, but you don't know what the group is. Let's now turn it round and come from the other side, so harking back a bit more to that theorem on random generation I showed you at the beginning, and think a bit more about bounds using the structure of the group, where you assume you know something about the structure. So then you should be able to prove much better bounds. So, those results I showed you on minimum generation, you'd prove some structural results about subgroups of symmetric groups and subgroups of finite matrix groups to bound this chief length term, and you get the bounds you want on the random generation. Let's go a bit more abstract. So now G is just going to be a finite group, and N is going to be some normal subgroup, some subgroup I can quotient out by. If you look at the probability of generating G, you'll find that it's completely dominated a lot of the time by the probability of generating that quotient. So, for example, if you're wanting to generate the whole symmetric group, that's all permutations on n points, you may know or remember that inside that there's a normal subgroup of index 2 called the alternating group, which is all the even permutations. So I've got a little cyclic group of order 2 sitting on top there. My probability of generating the symmetric group, therefore, never can go above 3/4 with 2 elements, because if I'm trying to make the cyclic group of order 2 and I'm picking 2 elements, I might pick the identity twice over with probability 1 and 4. So that's capping the whole thing somehow. The alternating group, we know from the result on the first slide, has probability tending to 1 because it's simple, but then the symmetric group is stuck at 3/4. That's messy. So we define our way outside the problem. We write P, and then this slightly clunky notation, I'm afraid, subscripts G and N. So I've got my group G, my normal subgroup N, of D is the probability that D random elements of G generate G, given that they definitely generate the quotient. So if I was working with the symmetric group, I would assume that at least one of my D random elements didn't sit in the alternating group. I wouldn't assume any more than that, but one of them has to sit outside. Okay, I might skip this other than to say this little bit is saying that the probability of generating the whole group, given that you generate the quotient, this conditional probability. Don't worry too much about what this is, but the key words to remember there are maximal subgroups. It's dominated by something depending on the maximal subgroups. So the maximal subgroups are the biggest subgroups inside the group, the ones that have no other subgroups bigger than them other than the whole thing. That shouldn't be surprising to you, because if I'm picking random elements of a group, if they don't make the whole thing, it's probably because they're inside some subgroup and they're going to make some subgroup instead. So that's what's going to dominate. So, simple groups. Not just simple groups, almost simple groups. Almost simple groups, they're things like the symmetric group. You've got a simple group and then you've just got a little bit of noise on top. A little bit of decoration on top. The simple group inside you is called the socle, so S is the socle of G. Well, we went back and looked at the theorem that I showed you on the very first slide about the probability of 2 generating a simple group tending to 1 as the simple group gets bigger and bigger. And we wanted to use that for computational purposes. Problem is there's no numbers. Knowing that it tends to 1 doesn't help me write any code because I don't know how quickly it tends to 1. I don't know what the lowest probability I'm going to come across is. Well, there was a conjecture of Derek Holt that the worst case was the alternating group on 6 points, so we set out and managed to prove that conjecture. So if G is a finite, almost simple group with socle S, so this includes all the simple groups, but it includes some extra ones as well, and G is 2 generated, all of the simple groups are 2 generated, not all of the almost simple ones are, then the probability of 2 generating G, given that you generate G over S with 2 elements, is certainly no less than 53 over 90. 53 over 90 occurs exactly when you've got the alternating group on 6 points or the symmetric group on 6 points. So there is no finite almost simple group, apart from non-abelian almost simple group, with worse probability than 53 over 90. And in fact, we were able to classify exactly the ones with probability no more than 0.8 and exactly the ones with probability 0.9. And the useful thing is that there's not too many of them. So this is actually computationally helpful. If you're not in these cases, you can assume that your failure probability is no more than 1/10. Well, I've got a 2 generated assumption there. I said that not all almost simple groups are 2 generated, so I can't always make them with just 2 elements. I can always make them with 3 elements. So going through the proof again, one can do 3 generation, and there you get that the probability of generating G, given that you generate the quotient, is always at least 0.92 once you take 3 random elements. With equality, if and only if you've just got the alternating group on 5 points. Okay, let me finish with a little application. So the Eulerian function measures the number of d-tuples that generate a group. So not just can I generate it with 2 elements, but how many pairs of elements generate it. Not just can I generate it with 5, but how many 5 tuples generate it. We write hg of d for the largest h such that I can make a direct product of h copies of g, so g, 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 and I can still make it with d elements. For example, if I take z2 to the d, so that looks like a vector space. I've just taken a finite field with 2 elements, dimension d. I need, with d elements from that, I can make a d-dimensional vector space. So hz2 of z is just d. Rather famously, the maximum number of copies of A5 I can make with 2 elements, you think maybe not so many. I'm only picking 2. How many direct factors can I hit with just picking 2? Turns out I can make 19 copies of A5 by just picking 2 elements. So I'm going to have an element from H5 in each of, from A5 in each of my 19 coordinates, and if I do that very carefully, I can do the lot. Well, Philip Hall, all the way back in 1936, observed that for a non-abelian simple group, the number of copies of it that you can make with d elements is equal to the number of d tuples that make the whole thing, divided by this alt s. That's the number of automorphisms of the group. That can very easily get turned into the probability of generating S with D elements multiplied by the order of S to the D divided by alt S, And Jim Weigold, in a long series of papers, was interested in the question, how quickly does this general formula HS of D grow? So he asked a while ago, the late 70s, I think, whether, given two elements from a bunch of copies of a finite simple group, whether I can always make at least root S copies of that simple group or not. Well, that got answered just recently by Attila Marotti and Chiara Tamburini. They showed that it was at least twice the square root of S. But in fact, using the thing I just showed you, it's not at all hard to show. It comes out in like 3 lines. That if S is non-abelian and simple and D is at least 2, and alpha is that horrible number, which is at least 1.029, then the number of copies of S I can make with D elements is at least that horrible number times S to the D minus 1 divided by log of the order of S, with equality if and only if I've got 2 elements from something called PSL34. And that's going to be asymptotically best possible because you can hit it with a family of finite simple groups called PSL2 over the field 2 to the I. Little extra calculation to match the original question that was asked by Jim Weigold. So in some sense this is a bit silly because this is the wrong shape for it. It shouldn't be looking like square root of the order. It should be looking like group order divided by log. But anyway, if you want to do his kind of asymptotics, you get that band. That's all I wanted to say, except to thank the organisers once again for organising such a lovely workshop. Thank you very much.
Thank you very much, Holger, and apologies again for making you a Aussie.
Had a lovely time there.
Questions? Yes.
I wonder whether there are, what applications there may be to this. I mean, I can imagine it having all kinds of applications in terms of motion, of robotic motion or something, but is there something that you have in mind?
Well, I mean, the computation with finite group theory was being used in the AI stuff I was doing. So, for example, they needed to be able to work with quite big permutation groups when they were doing things like scheduling shifts in hospitals. We were talking to the NHS. So you're trying to find, arrangements of nurses and doctors and that kind of thing. There's symmetries involved because, well, your nurses probably don't think they're interchangeable, but the NHS thinks they're interchangeable. So you want to find efficient solutions. So real life situations quite quickly involve working with very, very big groups on computer. To be fair, they're mostly permutation groups, not matrix groups. But I think the desire to do so well with matrix groups is partly that it's irritating that we can't, and partly that they do come up in physics, which aren't more. So being able to work with, in particular, finite matrix groups over, say, the complex numbers, but drop down to a finite group inside that is really, really important. And the next stage of the matrix group recognition project is working with finite groups over infinite fields rather than finite groups over finite fields. So, yeah.
What will happen for the matrix groups rather than a field and overall division rate? If we consider a division rate was well, the minimal generation C?
I think there are some people that work on them, but not as far as I'm aware of is there very much computational stuff going on with them at the moment. That maybe is one of the things we should look at next. So yeah. It's a good question, but I don't know the answer.
Any more questions? Okay, well, I just want to thank all the speakers, all the participants, everybody for being here and actually making it really enjoyable 2 days for all of us, including me. So thank you very much.